came out weak.
Okay. We're going to learn the second of the major techniques today, and we're actually going to start the second half of class. Trig scares people in calculus. We know that because our trig identities and our absolute knowledge of trig is probably not as strong as it is of our algebra concepts. So when it comes to trig stuff, sometimes we're a little bit iffy. But whenever we have trig stuff, like last day, we did use substitutions on trig things to make them look happy. In other words, we took a problem of this nature here, and by calling sine x my u, this became u cubed du, which all of a sudden was very friendly and refreshing and comfortable, and everyone's, okay, because this guy's easy. This guy looks scary, this guy looks easy. So we took things that were ugly, we made them simple. Could you imagine ever taking something that looks simple and making it look ugly by making it triggish when it wasn't? I mean, that seems completely insane. And that's today's lecture in a nutshell. We're going to take things that are algebraic in nature and substitute in the other direction, which seems, again, really, really wonky. But it's a kind of substitution you're not really familiar with. So I'm going to go back to a Calc 1 problem that we do that troubles people because it looks different. And it's going to be really the main form of substitution we do is not a U sub. U sub is a very, very special case. The main form of substitution we do is just the opposite. So this is from Calc 1 right here. I'm going to ask a couple of simple questions. I do this in Calc 1. At first glance, these three integrals look kind of the same, don't they? But that one in the middle looks a little more complicated. So two of these integrals really are quite the same. But it might not be the two you're thinking. It's actually the first two. The first two are really the same question. The third one is the one that's different. So in the first case, you can't integrate this. But if you said let u be x minus 2, then du is simply 1 dx. This is what is called a linear substitution. A linear substitution is absolutely the easiest one to perform, but often it's the hardest to recognize. It's the easiest to perform because your chain rule factor is always going to be a constant. In this case, it's 1. I mean, that's as friendly as it gets. So this would be square root of u, or u to the 1/2. Then I do 2/3 u to the 3/2 plus c. So 2/3 x minus 2 to the 3/2. Beautiful. Now look at the next one. If this is my u, then what's my du? 2x dx. Do I have that sitting around? Almost. What if I do this? Is that legal?
Yes.
It's only legal if it's a constant. It's not legal if it's a function or a variable. So now this is of the form 1/2 u to the 1/2 du. So this is exactly the same as the first one, isn't it? Oh, okay. So my final answer is going to be 1/3 u to the 3/2 plus c, or 1/3 x squared minus 2 to the 3/2. So I said two of them really are the same problem. Did I miss something?
Half. One. Or wait.
I already did.
Oh, you did.
Okay. See, that was 2/3, so that's why that's only 1/3. Now this one, let u equal x minus 2, then du is 1 dx. Oh, that's just like the first one. So obviously this is going to be x times u to the 1/2 du, right? I'm winking with my left eye, so you know. I mean, Austin just knows there's something up, right? That's right, isn't it? You don't like it? Why don't you like it? Well, first of all, it's impossible. Secondly, it's completely incorrect. And thirdly, if I have two variables in the integral at the same time, that means it's a three-dimensional problem. They're both independent, and it's not even from the same universe. No. You know, as we say at my house, you can't get any wronger. It's a word. You cannot have two variables at the same time. When you're doing a substitution, there's no such thing as a problem that creates two variables at the same time. So if you're doing a u sub and you ever look at your integral and you have an x and a u in the integral at the same time, not only is it absolutely incorrect, it's impossible, absolutely impossible to get the right answer because you made them independent, which means they can actually, don't write this down, don't write this down. In this case, I can factor the x out. In this case, I can factor the u out. It's treated as a constant. That's Calc 3. You can never factor a variable out of an integral. You can only factor constants. But whatever variable isn't this is treated as a constant with an integral. You learned this in Calc 3, which means every time you ever wrote two variables in the integral at the same time, it's not possible to get the right answer because you change the nature of the problem to a three-dimensional problem that really isn't even similar. In other words, it's just really bad math. That's really bad math. But how do I fix it? And where is my eraser? How do I fix it? Now, if you're in my class, we did this problem. It's not clever. It's more like survival. It's right here. If u is x minus 2, then what's x? Come on, somebody.
U plus 3.
How about u plus 2? Oh, so could I write this as u plus 2, u to the 1/2 to u? Yeah, in fact, it's the only way to do the problem. This is, some people refer to this as a reverse form of substitution. Actually, no. U substitution is a reverse form of substitution. From this day forward, the vast majority of all substitutions you will ever do in a calculus sense will be of the form, let x be some other function, and then what's dx? 1 du. Now, I'm going to hit the same thing, aren't I, in terms of the end. But the substitution, I'm going to let x be a function of something else. Now, we have another couple days, I think 2 more days. That's going to be the primary form of the lecture, all the infinitely many versions of let x be a function of something else. Then I replace the instruction dx with something else du, chain rule factor. But it's not backwards of u substitution. U substitution is actually backwards of this. U substitution is very special. But the limiting part of u substitution is if I don't have the chain rule factor as part of the original integral, it's not possible to do the problem. But in this case, I don't have to have the chain rule factor. I am creating the chain rule factor. In this case, it was a 1. But today we're going to do it with Triggish things. So this I distribute, I integrate, and it looks very different from the other two. But it's the only way I can do this problem was to do this. So now, we're going to look at problems that have the following forms. These are the forms I'm going to look at within a problem. I have integrals with the following forms in them. Now there's something called a table of integrals that every calculus book has, and most of them are things of this form. And the forms are as follows. A squared minus x squared, a squared plus x squared minus a squared. Very specifically, sums and differences of squares where it's the variable squared. Now, it seems like there should be one more, right? Well, what would the next one would be x squared plus a squared, which is the same as the middle one. So there's 3 different forms for sums and differences of squares. I have an integral. Maybe this is in the numerator, maybe this is in the denominator, maybe one of those terms is under a square root. But I don't know the antiderivative of that integral. It's not an antiderivative formula that I already know. So I need to do a substitution. Now, I'll give you an example. I wrote down a few problems today. We're going to do a few different versions. The first problem we're going to do today, and I'm going to come back to this in a moment. I'll erase it. We're going to do this one. Now, I would love to do a u substitution. The only possible u I can have is the argument. That's a 9, by the way. The only possible u I can have is the argument 9 minus x squared. So if that's my u, then my du would be something times x. I have an x. Except, where does that x need to be? Can a chain rule factor come from the denominator? No. That's absolute no, period. No explanation. No, it's a chain rule factor, which means it'd have to be multiplied by x, which means that x would have to be up here. So it's not possible to do a substitution there, not a u substitution, because I don't have the chain rule factor. I can't create one. Oh my gosh, what do I do? Well, it's one of these 3 forms. So I'm going to come back to this in a moment. I'm going to erase it now. The substitution we're going to make is something Triggish. Now think of your Pythagorean identities for a moment. What does sine squared x look, I'll say theta. What does sine squared theta look like? What does tan squared theta look like? What does secant squared theta look like?
Thank you.
Now think of the other side.
1 minus cosine.
1 minus the square of the cosine. Okay, how about tan squared?
secant squared minus 1.
Good. Secant squared minus 1. It is good to know these. And secant squared?
1 plus tan squared.
So it'd be 1 plus tan squared. If I have an integral that involves one of these three forms, I want to make the substitution let x be either sine, secant, or tangent. Which, again, feels totally backward that I'm going to create a situation where I have triggish things. But in doing so, I may get something that's actually not too terrible. Okay? Now, that a squared there, that's not going to be a 1 most of the time. Okay? It's not going to be a 1. So the substitution I'm going to make here is let x be, well, which of these does it look like? Well, this looks more like 1 minus, doesn't it? So what I'm going to do is I'm going to say let x equal something sine theta. I'm going to do that. Here's why. Because then what is a squared minus x squared if I do that? That would be a squared minus a squared sine squared theta. And you just said, well, then that would give me do you agree with that? By the way, you're rarely ever going to have a 1 there. When you learned your inverse trig, antiderivative, and derivative formulas, you always did it without a 1 just to get a kind of a general case. There are 3 Pythagorean identities. Doesn't matter which side the sines and cosines are on. That's, you notice I didn't say cos squared plus sine squared equals 1. I want to have one of them isolated so the other side looks like a sum or difference of squares. In this case here, if I made the following substitution, then this would become this, which is this, which is this. And why is that a good thing? Because if that statement lives, let's say, inside a root or as big raised to a power, this is no longer 2 terms. This is now 1 term, isn't it? Let's suppose I had to integrate the square root of this. Well, then I'd be integrating the square root of this, which would actually be quite easy. Does that make sense? Oh, yeah, that's not so bad. Now, if that's the case, I'm not going to go through the derivation. What do you think the substitution in the next one should look like? Well, that's one involving, right? What looks like, if it were 1 plus something, isn't that 1 plus tan squared equals secant squared? So in this case here, I'd want to let x equal tan theta. But because of that a, we'll call it same thing. Which only leaves 1 more. What do you think this one's going to be? I'm just kind of lining them up with a secant theta. If I have an integrand that I cannot integrate, okay, I cannot integrate. Here's what I mean by I cannot integrate. Somehow I got stuck on green today. Actually, let me put a number in there. Let's say I've got 25 minus x squared dx. Are you going to do a substitution on this? Or are you just going to integrate it?
You could just integrate it.
Yeah, please tell me you're just going to integrate this. To the 3 halves. Can't integrate that. Now I would need to do a substitution. I don't have a chain rule. So how would I do this? Like this. In fact, mathematically, it's the only way that I can get through a problem. So we're going to do a few different problems of all the different forms you can see so we can navigate and so you can see how it works. In the end, you're going to be integrating things you already know. Now, some of the stuff I do today will feel like really, really old stuff that you did a long time ago, before even calculus. And there's always a comfort when we do that kind of thing. So I said the first problem we're going to do this one. So of the 3 forms, does this look like a sine, a tangent, or a secant substitution, do you think? Only one person? Cece speaking for the group here. Yeah, it's going to be the sine because it's something minus x squared. Now, do you see a 9? No, you don't see a 9. What do you see? You see 3 squared. Why do I have to see 3 squared? Because if I use 9 in the problem, it's not going to work. Remember, it's a squared minus x squared. So even though I wrote a 9, you have to see it's 3 squared because it's 3 that you're going to use. So my substitution is going to be let x equal 3 sine theta. Which when I rewrite this, it'll be 100% trig-ish. But I can't have an integral of theta's dx, so therefore what would dx be? Yeah, derivative.
3 cosine theta,
3 cos theta
d theta.
integrated with respect to theta. When you're writing this, you're saying the integral of this equals the integral of this, which means within that integral, I'm replacing this instruction with this instruction. And when I do the substitution, it is all at once. It's not piecemeal. If I write an integral with thetas and x's at the same time, it's wrong. But I got the right answer. No, you wrote multiple answers because that thing won't equal the original problem and that thing won't equal the final answer. So you have, that's kind of like circling all the bubbles on the true false or the multiple choice and saying, but I got the right answer. No, you got multiple wrong answers. Yeah, if I try to mix variables, and by the way, there's no human being who has ever shown that as a technique. I know that. We come up with that all on our own or some really, really bad YouTube video. But no, it's all at once, and this one's not so bad. So my denominator will look like this. 3 sine theta, square root of what? 9 minus, what's the square of this?
9 sine squared theta.
Which I actually like. Now what about the dx? Well, that's going to be 3 cos theta, and my new instruction is theta. D theta does not go in the quotient. If somebody ever showed you to put your instruction in the quotient, then you made it an algebraic quantity. And by the way, if you can do that, let me write something really simple. If I make dx an algebraic quantity, then it commutes. And it makes all integration really easy. You know why? Because the answer to this is x plus c times f of x. I can do every integral that exists if you allow me to treat dx as a function or a scalar. You can't. It's not part of the integral. Remember, you learned this. There's a blank here, it's called the integrand. This symbol says I'm going to integrate, this symbol says with respect to x, and then I put the integrand in there. This is not an algebraic quantity. It is not in any way connected algebraically with that. It doesn't show up in a quotient, definitely doesn't show up in a denominator, but people will write that. It's actually bad mathematics, because the moment I put this d theta in the numerator, then I can absolutely algebraically move it all the way in front. Lest we forget, a over b equals a times 1 over b equals 1 over b times a is an absolute always true. If I'm putting my dx up here, then it is equal to this, and it makes integration so much easier. Wronger, but easier. Now, I know a lot of you weren't told that in Calc 1. In fact, it's a disservice to you to not tell you that something is absolutely incorrect and then allow you to do it. It won't work. It's not true. These don't commute. So keep it out there. Now, I'm going to deal with this guy next. 9 minus 9 sine squared is 9 times 1 minus sine squared, correct?
Yes.
And the reason you did this very specific substitution is what's 1 minus sine squared now?
Cosecant squared.
How about just cos squared?
Okay. No, sorry.
That'd be
Cosine.
easier. All of this is under the square root. Is that a good thing? That's a great thing, because that means the next thing I write won't have any square roots, but it also won't have any sums or differences. There's going to be mad canceling going on in a moment. Do all your canceling at once. If I start canceling and then write something and start canceling, it starts getting a little difficult to keep track of. So right now my denominator is 3 sine. Square root of this is 3 cos. Now do your crazy canceling. Does anything cancel? Yay? Nay? Yay. I'm going to put the 1/3 on the outside because I don't want it to get in the way. Way too often, and even in the highest levels, we see a coefficient and it's sort of in the way. It's confounding. We want to include that in our final answer and have the process. No, the coefficient is multiplied by my final answer. It doesn't really have a say in what I'm going to do next. So what's left? 1 over sine? Which is my absolute favorite function, right? Yeah. No, I hate cosecants. But can that be integrated in one step without doing anything? Yeah, we have an antiderivative formula. It's ugly. And this is why you have your integral sheet right in front of you. How many have an integral sheet right in front of them, by the way? Yeah, probably every hand. Unless you know this off the top of your head, what's the antiderivative? Which, by the way, if this was Calc 1, you actually...
Negative ln, or what?
No, not negative.
Natural log of absolute value of cosecant minus cotangent.
Yeah, by the way, arguably the ugliest of all the antiderivative formulas. It is what it is. Okay. But we're done with the calculus. I'm sorry. I got a boo-boo here. I got a boo-boo. What's my boo-boo? Theta. If that were an x, I would have been done. But that wasn't an x. Oops. Will we write x's there? Oh, yeah. Okay, now I'm done with the calculus. Tell me about my final answer. It ought to have x's in it. It'd be kind of like when you do a u substitution and you do perfect integration and you said, and the answer to my question is something u-ish. Don't you need to substitute back to x if it's an antiderivative? Okay, Houston, we have a problem. How do I get back? We've done everything right to this point. But if I put x's in there, then I'm done. It's incorrect, but I'm done. Well, this is the part I said this will feel very old. You did this in baby trig, free calculus. I'm gonna do a really simple old trig problem. Remember something like this? I'm gonna tell you that the cosine of theta is 3/4. I want you to find the other 5 trig functions. Now let's say that theta is in the first quadrant. Okay. How in the heck do I do that? I'm going to remind you. Draw me a picture where the cosine of theta is 3/4. Will that work? So what goes here?
First, 16 minus 9, so root 5.
16 minus 9 is a root
5.
7. Yeah, close. So what's the tangent of theta? Root 7 over 3. Oh, what's the sine of theta? Root 7 over 4. You guys remember doing stuff like this? You drew a picture, you filled in the blanks, it was a piece of cake. When you did your inverse trig derivatives last semester and you were trying to figure out, you did the same thing. How am I going to solve this? It's right here. Can you draw me a picture? Can you draw me a picture where x equals 3 times the sine of theta? Yeah, but think of it this way. How about if I say it this way? Sine theta is x over 3. What does that picture look like? X, 3, and what goes here?
Root 3, well, 9 minus x.
3 squared or 9 minus x squared. Oh, there's a root 9 minus x squared in the question. Do you think that's a good thing? That's a really good thing. By the way, this is the pathway on every problem that exists that we're going to do this type of substitution. You always go back the same way. You draw your triangle, figure out what your relationships are. So now I'm done with the calculus, but I need to substitute back. In my picture, what is the cosecant of theta? Well, if sine is x over 3, then cosecant is 3 over x. If tangent is x over root, then cotangent is the root over x. Now, anything else? Well, can I do something with that?
Yeah, the denominator is the same.
Yeah, I probably would be better served putting that as one quotient. But that's not a calculus step, that's not an algebra step, that's not even a log step, that's just adding 2 things with the same denominator. I would probably say, you know what, if I write it like this, it's just a little bit less stuff. I always say, if you're gonna do this on your calculator, which one would you rather do? Probably less stuff. That's it, that's my final answer. Wow. How can I check that I did everything correctly? Take the derivative of that. And if I take the derivative of that correctly, I should get this integrand. Do you think the derivative of that's going to be trivial, or do you think that's going to be a monumental pain? You've got the log of a bunch of stuff. Ugh. This is where I cheat. This is where I'll go to Wolfram and say, take the derivative of that. And it will say this, and then I know I did it right. It's always good practice to take the derivative. But you're saying, I'm pretty sure I did everything right. Is there any place here where something could have gone wonky? Always. So I'd really like to know that I did it right. So I'm lazy. I'd go to Wolfram and say derivative of this, and it equals it, doesn't take very long. And then I know I did it. Don't do the antiderivative of the original question, because you're going to get multiple answers. And the funny thing is, the right answer might not actually be one of them. That's the weirdest part. Sometimes the right answer isn't actually one of the answers. Yeah, because sometimes the Wolfram can probably do 2/3 of the problems, but not all of them. All right, let's try another one. If my numerator were an x, would this be a simple u sub? Because if you were doing a u sub, you only have one choice of the u. What would it be? Now, by the way, that's not a trick question when I say you only have one choice. It would have to be 36 plus x squared. Because that's the only function in there. And so if my numerator were just an x, could I do this as a simple u sub? Yeah. Or what if that were an x cubed? Then this would be a really simple u sub. But it's not. So this can't be done as a u sub no matter how hard I try. Can I do this as an integration by parts? I could try, but because my denominator involves a sum of squares, what we just did, which is actually called trig substitution, by the way, since my denominator involves a sum of squares, trig substitution is going to be way cleaner. It may be possible to do this by parts. There are a lot of problems that we're going to find that are crossovers, that the techniques you're learning, more than one technique might apply. But sometimes one of the techniques may be really long and difficult, and the other one really short and sweet. No, I definitely go for trig sub here. Now, this is a squared plus x squared. So which of the subs am I going to use? Sine, tangent, or secant? By the way, you notice we didn't use cosine, cotangent, or cosecant? Why do you suppose that is? We could have, couldn't we? There's actually a really simple rule of thumb. We generally go with the sine instead of the cosine. We go with the tangent instead of the cotangent. We go with the secant instead of the cosecant. Because the derivatives of the cofunctions are all negative. And do we sometimes make mistakes? Yeah, differentiating sine, hardly anybody makes a mistake. Differentiating cosine, we sometimes forget the negative. The derivatives of the cofunctions are the negatives. And then everything else actually works, and you're going to get the same final answer, but there's an algebraic step that sometimes we mess up. So we go with not the cofunctions, the ones that don't have negative derivatives. It just makes our life a little easier. You could have said in this problem, you could have said let x be 3 cosine theta, and done the entire problem from beginning to end, and you would have got the same final answer. There would have been a little bit more involved. So here, I'm going to let x equal, first thing I do, and I actually do this. Very first thing I do, because if I didn't write 3 squared and I put a 9 here instead of a 3, none of the algebra would have worked, would it? I mean, I wouldn't have been able to do this. I'd have been fudging. So x is going to be what? 6 tan theta. Because a squared plus x squared, we said that's the tangent substitution. What would my dx be?
6 secant squared.
Secant squared, yeah.
Theta.
We want to get that right. One of the things we actually like about this form of substitution, let x equal another function, I don't have to have the chain rule factor. I'm creating it. So there are really no rules in terms of what does the form look like. We're going to find this over time. We're going to do a lot of problems, not just trig, but all sorts of things, where x literally can be any function on planet Earth. And then I replace dx. Now, it always works. Now, the new integral you get might not be easier. So the choice you make is designed to make the problem easier. But just for fun. I could have said let x equal, I don't know, theta cubed. Let x equal e to the theta. Let x equal log theta. Just pick any function you want. I can do this from beginning. I can do this whole thing and I get a whole new integral. Now that new integral may be worse than the original one, but it's legal. It might not be efficient. But this form of substitution almost has no rules. You're making your choice based on what you think is going to make the problem easier. And like I said, in a week or so, the entire lecture will be devoted to all the different types of problems we're going to look at, where if I make this form of substitution, I took a problem that looked impossible and made it, I don't want to say easy, but certainly doable. When I do this, the idea is my new problem is going to be better because I will no longer have a sum. That's the key. When I make the trig substitution, my denominator won't be a sum anymore. So when I do that, this new problem is going to become x squared, so 36 tan squared theta. My denominator is going to be 36 plus 36 tan squared theta to the 3/2. My chain rule factor, and now I'm integrating the whole thing with respect to theta. If there's a common mistake, it's not the part on the right. If there's a common mistake, what do you think it is? Forgetting the chain rule factor. It's doing everything but forgetting to put the chain rule factor in. I still might be able to finish that problem. In fact, I can probably finish that problem, but it's going to be a different answer because it's a different problem. Now, let's get this part before you go on. 36 plus 30. The fact that those are the same numbers, that's a good sign. If these numbers were not the same, then I cannot factor it out. It means I made a mistake. It means it's not going to work. In the last problem, if I had inadvertently said 9, then I would have had 9 minus 81. And that wasn't going to factor, was it? Those constants have to be the same number if I did it right. So this is 36 times 1 plus the tangent squared. And what's 1 plus the tangent squared?
Secant.
The secant squared. Oh, that's beautiful. So now I have 36 secant squared. Or if it helps you, how about if I write that as 6 squared secant squared? And I'm raising everything to the 3/2. What's the rule of exponents there?
You square root it and then cube it.
Multiply them. If it's x to the a times x to the b, I add them. If it's x to the a, so I have something to a power raised to a higher power, I multiply. Oh my goodness. So I'm multiplying 2 by 3/2, which is 3. Is that a good thing? It's a great thing. You notice it's 3/2, not 3/4 or 3/7. The only problems you're ever going to see are going to have integer exponents or halves. It can't be anything else, because if I did, let's say, cube root, those squares aren't going to help me. Cube roots of squares are not, they're not friendly things. I need square roots of squares, right? So I'm going to rewrite this now with my new friends. Hide here. So my numerator is, I'm not even going to bother multiplying those out yet, because I know numbers are going to cancel. Yes, I could multiply the 6 and the 36, that's fine. I now have 6 cubed, and I have secant cubed of theta. That's ugly theta. Okay, y'all with me on that? And then d theta. Let me get rid of this stuff. Now stare at that for a moment, make sure you believe it. We haven't really done much calculus. That was all the calculus we've done. We're just substituting in, but making sure we have the right things. So I have something that I wrote as a square, and I'm raising it to the 3/2 power, so now everything's cubed. Do I get any canceling?
Yeah.
How about the coefficients? Do any of them cancel?
Yeah.
They all cancel. Oh. That makes me happy. What else cancels?
The secant cubed and the secant squared.
Ooh, that whole thing and all but one of those. Now, this is what I have. I have no more coefficients. I like that. I now have tan squared theta over secant theta. Now, you know the rule of life, changing everything to sines and cosines, but in this case, is that going to help me a lot?
No.
I'm going to have, well, if I move that to the top, I'm going to basically sine squared over cosine. I don't like sine squared over cosine. That's not really useful. So there's actually something simpler than that. And this is one of those things where when you practice a lot of trig stuff, these kind of things just sort of fall into your lap after a while. If the tan squared on top isn't useful, but what if it was a secant squared on top? Would that be helpful?
Yeah.
That'd be way more helpful. So why don't we do that? Wait a minute, what do you mean do that? Any ideas? Pythagorean identities?
Secant squared minus 1.
Oh, and now what? Secant theta minus the reciprocal of secant theta. Oh my goosh. I just made the problem really simple. By the way, there is no other route. This is the only route in existence, and if I don't see it, then I'm against, I ran into a brick wall and don't know what to do. You can't have trig functions in a denominator. That's just not going to help you. And we know the reciprocal of every trig function is another trig function. We know that. But the problem is, if I bring this up as a cosine and I cancel one of the cosines, it's not very helpful. It's just not. What I have left over isn't entirely helpful. So I use the fact that there's a Pythagorean relationship, and now I have secant minus 1 over secant, which is a secant minus cosine. And now, this antiderivative here is all of a sudden not so bad. So we talked about awareness of your trig identities. Knowing your Pythagorean identities and knowing your trig definitions, things like, the reciprocal of sine is cosecant. That's really useful to know because it comes up. Knowing that is all I needed to get to here. Do I know these both these antiderivatives? Yeah. What's the antiderivative of secant? It's a little less common.
1 secant theta
Plus tan theta minus sine theta. Ooh, I like that one. That one wasn't bad at all. So I am completely done with the calculus. There is no more calculus. But my answer is in terms of theta right now. I need it to be in terms of x. So I'm going to draw a picture. And the picture I draw is one where x equals 6 tan theta, or tan theta equals what? X over 6. In this picture, does the tangent of theta equal x over 6? Make sure you got things going the right way. Remember, sol katoa, this is where that comes in handy. Did I get that right? So what goes here?
36.
6 squared. Oh, I'm going to write it like this. Yes, it is 36.
Yeah.
36 plus x squared, but notice in my original problem, I have a 36 plus x squared. I have a 36 plus x squared. That's a good thing. It didn't somehow become something different. Yes, absolutely 36. Okay, so let me move this up to the top. So I have the log of, well, cosine is this over this, so secant is this over this. So that'd be 36 plus x squared under the root over 6 plus sine. I'm sorry, where are we in the part? Lost myself. Oh, I got that backwards, my bad. That's the cosine. That's the cosine, isn't it? The secant, if the cosine is this over this, oh no, I did have that right, sorry. Cosine is this over the secant is that, my bad. I did have it right. I should not second guess myself. Okay. And then the sine is what?
We wrote
Something doesn't feel right.
10. Wrote 10.
X over 6, we got that right. Oh, I'm sorry, I keep looking. I'm sorry, I keep saying sine. Yeah, Cece, you gotta be louder. Tangent, we're on tangent, aren't we? So what's the tangent? X over 6. That's funny, I keep looking at this guy, I thought we were done with that. We're not done with that. and then minus, you all agree with that?
Yes.
36 plus x squared. Now, look at the first term. Can we improve upon this? I'm going to give you a hint. I'm going to call that C1. Whenever we do things like calling something C1, what are we saying? There's going to be another C, yes. I'm going to show you a better version of this answer. By the way, everything I said is true and correct. And when you look in the back of the book, it won't look like that. If you're checking online, it won't look like that. It'll look slightly different because there's a slight improvement. First of all, look at my log thing. Don't I have the same denominator? So can't I rewrite that one as can I do that? Isn't log of a quotient the difference of logs? Isn't that just a constant?
Yes.
I already have a plus C1 and I have this. So what is the better answer? The better answer is the log without a quotient. Can't do anything with that guy. Now it was plus C1. Now it's C1 minus log 6. Why don't we just call that C2, or even be lazier than that? How about if I just call it C? You notice that's a C, that's a C. These cannot be equal. They have to differ by log 6. That's a better answer because my log doesn't have a quotient, which means if I'm doing this on my calculator or I'm graphing this, a little bit simpler to work with. Would you agree? Not having a quotient is always a good thing. Now, is this an absolutely critical life, changing moment? No. No, but it shows good understanding of the logarithms, that the fact that I could manipulate that. I didn't get rid of a term. I combined a term. I combined the negative log 6 with the plus C1. And there's a lot of problems that we're going to do throughout calculus and differential equations where things of this nature come up, where I have a constant, an actual value, and then an arbitrary constant. It doesn't make sense to say, and my final answer is 4 plus C. If C represents any real number and I'm adding it to 4, isn't that just some other real number? So I usually just condense it into one thing because it's just a little bit cleaner. Okay? Any questions so far? We're going to do one more.
So for the log, if you know the inside term is always positive, can you parentheses with it?
Even though the inside term is always positive, because that's applied, even if x is negative, won't 36 plus x squared be larger than x squared? No, so in this case here, if you remove the absolute value, would you be getting into trouble? I think that's really what your question is. Would you be getting any trouble in that case right there? Again, this is good overall alertness of what's going on. In this case, you would not. You would not, because even if x is negative, and by the way, there's nothing wrong in the original problem with x being negative, even if x is negative, x squared plus 36 would make sure the numerator was still positive. So could you drop it at that point? Yes. By the way, is it ever wrong to leave the absolute value in there when you're not sure? No, the only time I tell people don't leave an absolute value when I write, and the final answer is the absolute value of 6. Isn't that just 6? Yeah, it's silly to leave it when you're taking the absolute value of a number. Don't just write the number. But in a case where it's a quantity, the rule of thumb is if it's possible for that quantity to ever be negative, then you absolutely, no pun intended, you absolutely must leave the absolute value. But since that quantity you just argued can never be negative, you could drop the absolute value. Right? It doesn't cause a problem. And the safety thing is, if you really aren't sure, what should you do? What should you do with the absolute value if you're really not sure?
Keep it.
Yeah, because it's not going to be wrong. I do like it when I see somebody start with the absolute value and then remove it because they know it's a strictly positive quantity. I like to see that because, it shows overall alertness. It's not going to change your answer, but again, it shows you I really see what's going on here. All right, I got one more. Kind of nasty. Let's see. I got 1 over x squared times the square root of x squared minus 16. Now, this looks really close to something. What if that's just an x? What if that first term were just an x? Not a use of. It's straight up what? Inverse secant. It's a formula. It's actually a formula. Is that, would you say that's one of your more common or less common? Probably. Integrating to get inverse secant. Inverse tan is very common. Inverse sine is sort of, inverse secant's not very, but if that were just an x, that's the formula for inverse secant. But because that's an x squared, it isn't. And there's no u sub because there's no chain rule factor. So this is still a straight up, right, trig sub kind of problem. And it turns out there is no other way. If there was, I'd show you. And by the way, there are a handful of problems that we're going to look at that fall under multiple ways of doing it. And the rule of thumb is, if you're saying, well, which way should I choose? The answer is yes. Whichever way you see first. This is not an integration by parts. It would not be incorrect to try integration by parts, by the way. That wouldn't be a problem. But those x's in the denominators make the integration by parts a little bit sketchy because they're not getting better, are they? Each time I do it, it's not necessarily going to be a pretty one. X on top, I'm more comfortable with parts. X on the bottom, much less so. So I see a 4 squared there. Oops, so, no, I was going to write theta, sorry. Let x equal 4 times secant theta, because x squared minus a squared we said was the form of secant, because that's secant squared minus thing is tan squared. You're choosing this because that's the only one that will obey a trig identity there in that case. Yeah, I could do cosecant, but I don't want to go there. That's just too nasty.
Or secant theta, tan theta.
Beautiful. So when I do this, this is very busy. My denominator is going to be 16 secant squared theta, and then 16 secant squared theta minus 16. On top, I have my chain rule factor. Again, don't forget that. All integrated with respect to theta. What I like is the square root will be of one term. I can evaluate it, and then I'm probably going to get some crazy canceling all over the place. So in the end, I'm probably going to get something small, but it will not be sums. At worst, I'm going to have a quotient, maybe even only one term. Okay? So always go to this step next. So I don't like writing integral equals integral equals integral while I'm doing all of my algebra. I like to do all the algebra, simplify it, and then go forward. So I just do it right here. So this is 16 times secant squared minus 1, and secant squared minus 1 is
Tan squared.
tan squared. Aha. I now have the square root of 16 tan squared. I can do this. So I have the square root of 16 tan squared, so I'm going to have 4 tan theta. Does anything cancel? I'm pretty sure a lot of stuff's going to cancel here. Let's see. In terms of the constants, what should I do with that 16? I'd put it on the outside. Yeah, again, I don't want it to interfere, because sometimes we look at it and we can't tell what's going on. Now, I have a secant and a tangent on top. What am I left with after all of this?
1 over secant, which is cosine.
Is 1 over secant the only thing we have left?
Yeah,
Is that good?
cosine.
Oh, I don't know about you, but that makes me very happy. All of that horrible mess reduced all the way to this. Is it always going to reduce that small? No, but it will always reduce.
I was just curious about looking at the integral all the way to the left and the bottom. We had.
Did we lose something?
Tan squared theta.
Did I?
And I was just curious on the bottom because.
Oh, here.
Yeah.
It's the square root of 16 tan squared.
I see,
That's why I say always manipulate that part first.
Yeah.
Then when you rewrite it, you notice when I did the rewrite,
Yeah,
I didn't write this equals the integral, this equals the integral. Well, I'm simplifying this in multiple steps. I prefer to do it all at once. It's just easier for me to follow. Plus, to rewrite an integral without going any forward, right, we're just manipulating algebra. Yeah, it's time consuming. I'm lazy. So, what do we got? Oh, I like that. Now, how the heck am I going to figure that out? Go up to there. It's always the same way. Draw me a picture so that the secant theta equals x over 4. So where's x? Where's x? It's on
Hypotenuse.
the hypotenuse. Okay, I was waiting for that. The cosine would be 4 over x. The secant would be x over 4. So do I have that part right? So what goes here?
X squared minus 4 squared.
X squared minus 16. Is that a good thing? Yeah. You notice? Now, I want to point something out. Is it possible we could just look at this and see something else? Here's what I mean by see something else. You saw a difference of squares, and you already did one earlier, and you went for the sine function rather than the secant function. Can that happen? Yeah, it's an error, but it can happen that I said, oh, let x be 4 sine theta. Well, it's not going to work. It just won't work because when I try to get down to the Pythagorean identities, it's not going to work. And fact is that when I do all this stuff, I would probably have a 16 minus x squared over there somewhere, which is not the same thing. So if I did everything right, my original integrand, which had the thing that I couldn't deal with easily, shows up every time in that triangle. So what is the sine? The sine would be this over this. That's it. The check on this one wouldn't be nearly as nasty as some of the other checks you were looking at, but it still would be involved. It would not be trivial, okay? Please don't take a picture with me up here. Please do not do that. You can take a picture after class, before class. Yeah, that's one of the things I'm really, really skittish about. I have people doing that. It's illegal, first of all. You can't have your cell phone actually out at any point during a class. That's been a law since like 1991. But when people are taking pictures when I'm up here, you can't possibly take a picture of the board with me not being in it, and you legally can't take a picture of me without my permission in my classroom. You guys have to understand this. I've had people do this recently. I've had people try to video. You can't do that. You can't. You can ask me for permission. I'm going to say no. Plus, I got a video right there. But I've had people doing the click, 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 and they're like, oh no, I'm taking a picture of the board. And I go over to the camera, no, I'm in every single picture. Yeah, don't do that. Put your phones away. You can't have them out anyway. You know this. Okay, we've looked at, by the way, there's an infinite number of variations of each of these problems. But what you just saw were all the 3 types of problems because I did all 3 types of substitutions. They can only get uglier. The ones we did were not trivial, but at the same time our final answers weren't serious, right? Lots and lots of things. It is often the case that you may end up with something big. It's probably not going to be an integration by parts ever. It's going to be something, but maybe a little bit more involved. Now, there's a classic problem that we're going to look at twice. We're going to look at now and we're going to look at it later because there's 2 potential methods of solving this one. What if I had something of the form 1 over, let's say, x squared minus a squared? On the cover of every calculus book, you'll have all of your antiderivative formulas for Calc 1. Okay, you guys know what I'm talking about? Either on the front cover or the back cover, you see all your antiderivative formulas. But on most of the books, they'll have this as one of the first ones. And it always troubles people because they said, wait, that's not one of the ones I learned in Calc 1. No, you didn't learn that in Calc 1. We're going to derive this one right now, and it's not trivial by any stretch. But this is a problem that there's going to be another way we're going to learn later, like later on today, of how to do this that is completely different but will give us the same final result. So what form, what substitution do I want to make here? Now, by the way, assume a squared is probably a happy number. 1, 4, 9, 16. Could a squared be 7? Yeah, and by the way, does that change any part of the process that we did? No. No, it just means I'm going to have a root in my answer as opposed to an integer. That doesn't affect any part of the calculus. So if it makes it easier conceptually, just think of a squared as something happy. Because in the end, you're going to have an a in your answer. So it doesn't matter, right, if a is nice or not. What it does matter is you're going to choose a to be the positive square root, because otherwise you have to worry about two different answers. So if I wrote a 16 up there, no one's going to say, well, it's plus or minus 4. No, it's got to be the positive root, because the negative would then give me a negative for my chain rule factor and all that kind of stuff. So let's keep it simple. Let x equal a, we just did this one, secant theta. I think we're going to need to close the door. At least until they stop doing that. Yeah, we just get too much external noise. Now, there's nothing clever here. We just stick them all in here. So my denominator is a squared, secant squared, minus a squared. My numerator is, does that look right? A squared, secant squared. Yep, I think we're good there. Now, all of this becomes a squared times secant squared theta minus 1, or simply a squared tan squared theta. That doesn't look entirely friendly. I don't know. This might be one of those change it to sine and cosine kind of deals. I really don't want to bring tan squared up on top as a cotan squared. I don't think that's going to make it easier. What do you think? If we change this to sines and cosines, then I'd have 1 over cosine, that's my secant theta. When I bring the tan squared on top, I'd have cos squared over sine squared. Is this getting better or is this getting worse?
That part with it is a secant theta times theta, right?
Did I miss it? Did I miss that? Oh, yes. Man, good catch. We should have a tan theta on top. Oh boy. Woo! That saved us some time. Good catch. I always like it when people are alert. Well, that changes things a little bit. What do I have now? Actually, that makes it easier. So I'm going to get a tan canceling. I'm going to have secant over tan. Does secant over tan reduce? Actually, it does. When one of them's a square, you got to be a little more careful. Secant over tan, yes, this is where you use the fourth rule of life. Secant over tan. So that's 1 over cos over sine over cos. What does that give us?
Sine. 1 over sine.
Which is
Cosecant.
cosecant. Yeah, this is where the fourth rule of life is really useful.
Where does A go?
Well, no, I'm just looking at the trig part first. Yeah, well, we haven't finished yet. You all agree that's kind of the key here. If I don't get that right, the rest of it's not going to go so well. So after all that, what is this going to equal? 1 over a times the integral of cosecant theta, which of course is not our favorite. It is something, but it's not our favorite, but we'll keep going. And the antiderivative of the cosecant function is, I think we did this one already. Strangely enough, cosecant and cotangent come up often because when you have sines and cosines all over the place and you're canceling, you often end up with a sign on the bottom, that kind of thing. So this is what? Log of cosecant minus cotan plus c. Okay. I already know this is going to be ugly. So let's draw our picture and I'll put it up here. So secant theta is x over a. So x a square root x squared minus a squared. So far so good? So what do we got? So cosecant would be That's not something we should labor with.
X over square.
X over the root. So we go, I'm not gonna answer that one. No, that actually isn't calculus. That's, you know, that's not high level stuff. Cotan is A over the root. And now the fun will begin. Our final answer is not going to look anything like this, because we will be able to simplify this significantly. The only other time you probably did something of this nature was when you did the derivatives for the inverse trigs, and you were working things, and you, or I should say, when you're deriving the antiderivatives, and cosecant came up, and you were manipulating and conjugating and all sorts of crazy stuff. This one here, there's a logarithm, which means I might be able to apply a log property, but not yet. We know the sum of the logs is the log of the product, and the difference of the logs is the log of the quotient. The log of a difference isn't anything. But I do have the same denominator, don't I? So at least let's do this. This will get us started. So far, so good? And I do need the absolute value, because x minus a will be negative how often? Half the time, yeah. Now, so, well, aren't I done? You know, isn't x squared minus a squared a difference of squares? So can't that be factored? So off to the side, I'm leaving the logs for a moment. Can I write that like this? Let me ask you. Remember, the square root of a product is the product of the square roots. And if x squared minus a squared is x plus a, x minus a, then is that valid, what I just wrote? This is not simplified. I have the same term top and bottom. Can I cancel something?
Yeah,
Yeah, where will the root end up, CZ?
on the top. So root x minus a over root x plus a.
Okay, y'all with me so far? Tell me about the quotient of the roots. Isn't that the root of the quotient?
Yes.
Would that be the same as saying the quotient to the 1/2 power? And now I'm going to use the log property and pull the exponent out in front as a coefficient. By the way, do you like this better than this? I hope so. Using nothing but log properties and a little cleverness, this part right here is equal to this. But log of something to a power, the power comes front as a coefficient. By the way, I can't lose the absolute value because that quantity still will be negative half the time. Because x can be negative. Whoa. Now, this was not trivial. This is one of the longest derivations you're ever going to see. We're going to learn another way of doing this, and it'll actually be a lot shorter because we're a completely different technique. Okay, questions? All right, we're going to move on. Trig substitution is an extremely useful tool, and we use it a lot at this level. Strangely enough, the farther you go in math, it really is integration by parts as a major means of integrating is going to be the most common tool you use. From what I understand, because it's been a while since I had physics, but the physics teachers tell me this is the one they use in physics. You don't do much of any parts in physics, but you do a lot of the trig substituting in the 196, 197, things like that. Okay? Now we're going to move on to the next topic, which we're going to spend a couple of days on because there's so many different types. Okay? So you're in a baby algebra class. You're in a baby algebra class. And you have something like this. Let's say x plus 5. And you're told, hey, can you write this as one quotient? He's like, yeah, of course I can write it as one quotient. Piece of cake. So first of all, what would the common denominator be? Would it just be the product of these guys? Yeah, I mean, there's no common factors. So if you remember what you'd do over here, you'd say, we do x plus 5 over x plus 5, and then over here you do x minus 2 over x minus 2. And then what would you have? You'd have 3x plus 15 plus 4x minus 8, is that correct? And so now I've got, sorry, all these straight marks. So now I've got 7x plus 7 over x minus 2, x plus 5. Great. All right. So there's my answer. And so I'm going to go ahead and erase all this. And I said, oh, shoot, Austin, I really need the original problem. Shoot. What did I add to get these guys again? Oh, I erased it. See, going forward, you learned that actually in pre-algebra. I don't care about going forward. I want to go back. You guys remember that? It's called partial fractions decomposition. I'm taking something that was the result of combining things, and now I want to pull it apart. So this is something that you spent probably 60 to 90 minutes of your life in a pre-calculus class doing. And when you ask your instructor, why are we learning this? Did anybody remember asking that question? The answer was probably either I don't know, because they don't teach Calc 2, or you'll use it way in the future. You're going to use it now. The reason you learned partial fractions decomposition in pre-calculus is because it's a very common thing in Calc 2 and differential equations. And how many remember? Well, I've taught Calc 2 for a million years, and I don't think I've ever had a student who actually remembered it, so we're going to review it. And then you will all remember it and go, oh yeah, that wasn't that hard. So what we did was we did something like this. We walk you through the process. You said, I'm going to pull this apart. But I have no idea what the coefficients are, but I do know I can pull it apart. I absolutely know that because I can put these together. So we'll go, let's call that A and let's call that B. Okay. So I'm going to show you the general way of doing everything, and then I'm going to show you every shortcut that I would want you to take to get to the same place. Because there's a lot of extraneous things that we do when we're doing exercises, but if we don't remember all the details, we kind of need to do everything. So the first thing we would do is, let's take the right side and make it over one common denominator. That's the first step. So just like before, so we'd have A times x plus 5 plus B times x minus 2. Okay, everybody okay with that step? Now, the quantity on the far left and the quantity on the far right, we're equating them. But since they have the same denominator, then aren't we just equating numerators? And the only way I can solve this is to equate numerators. So the next thing we will write is that 7x plus 7 equals A times x plus 5 plus B times x minus 2. So here's what I'm telling you. Right off the bat, go directly to here. Go directly to there every time. Yes, this is the justification. But because you're equating numerators, it's kind of like saying multiply both sides by the common denominator. So I only want to look at the numerators. I could care less about the denominators because once they're the same, now I have two equations, I have two unknowns. The formal textbook approach, and which is absolutely correct, is to equate coefficients. So distribute, gather terms, so I have A plus B times x plus 5A minus 2B, and that is supposed to equal 7x plus 7. That means that A plus B must equal what?
7.
Actually, you can't mess this one up, can you? The coefficient in front of x has got to be the 7, and 5A minus 2B is the other one. I have two equations, I have two unknowns. Is this one fairly simple to solve? Yeah. In fact, most of us would probably just use the addition method. Yes, you could use a matrix. There's a whole bunch of ways. There's actually 6 ways. One of them is graphing. Don't do that one. Most of us would say, no, let's use the addition method. So how about if I multiply the top equation by 2? Then I'd have 2a plus 2b equals 14. And on the bottom, I have 5a minus 2b equals 7. And when I add them, I have 7a equals 21, so a equals 3. I can do one of two things. I can do this again to eliminate the other variable, or I can substitute this into one of the equations. Which would be easier? I think substituting this in is a little easier. And when I do that, what will I get? B equals 4. So now going back to the original problem, I can say that this is equal to 3 over x minus 2 plus 4 over x plus 5. Do you all agree with that? Now, this is the easiest, absolutely by far the easiest of all the types. When you have linear denominators. There are 3 types of problems. We're going to look at 2 of them today, and the more complicated one we're going to look at next day. And the more complicated one is the one that every textbook ever written on the subject does completely incorrectly. Meaning it could take you a week to get an answer that I want you to get done in 30 seconds. But when you get to differential equations, these come up again, and the authors of those books show you the right way of doing it that you're not shown in a calc book. There actually is a technique that is important, probably the most common one, in case you forgot, the one where I have a repeated denominator. It's the worst one. And it can be very long because the formal textbook approach, it's not that you'll get a wrong answer, it's that you can't get an answer anytime soon. And if you don't know matrix algebra, it's actually impossible. Because you often will have as many as 5, 10, 15, 20 variables, that many equations. It's a very unnecessary technique. Now, everything I said was true and correct, but there's a way faster way. So if I'm going back to baby algebra, and I said this statement is true, okay? I'm saying this is identically true for some value of a and b. That no matter what x is, there's only one combination of a and b to make this true. So rather than try to solve for a and b abstractly like we did, there's an easier way. And that's choose values for x. I have to get 2 equations and 2 unknowns. There's no way around it. I have to do 2 equations and 2 unknowns. But what if I said, why don't I choose? I don't know, how about if I start with I choose x to be
-5.
Oh, okay, I was going to do that second. What if I start with, let me choose x to be 2. So what does the left side equal?
21.
7 times 2 plus 7 is 21. What does the right side equal? Well, that would be 0.
7A.
That would be 7a, and that implies that a equals 3. And what would another really good choice? I heard someone say it. If I choose x to be -5, then the left side would be -14 plus 7, that's -7. And the right side will be -7, sorry, did I do that right? If x is -5.
-28.
Oh, I can't add, it's not -7, be -28, thank you. And the right side would be -7b, and that would give us b equals 4. Same results? Faster? Yeah, better? Yeah, here's why. I gave you 2 linear denominators. What if I gave you 4? What if I gave you 8? What if I gave you 12? This is still this fast for each one. The other one, that's how many variables and how many unknowns, which means once you get past 2, you cannot possibly do it without using matrix algebra. And if you haven't been doing matrix algebra recently, are you going to remember matrix algebra? Probably not. You shouldn't need to have to use matrix algebra to answer this question, but you have to answer this to finish. So how many, by the be honest, how many learned this, what I just said, where you're substituting numbers in? By the way, this is the way, my experience is most people learn this. I was taking a class, a graduate stats course, I think it was a probability course many years ago at San Diego State. And the instructor, very smart instructor, but he wasn't very efficient. So he would take forever to do processes, and I'd be waiting for him to get the answer because I've already got it. So we were doing one, it was a really gnarly problem using what are called moment generating functions in a class, and he ended up, it was a partial fractions decomposition in order to answer it. And he's going on, and get to the end of the class, he goes, sorry guys, we'll have to finish this next day, it's just too much. So I said, can I talk to you? So I went to his office, I said, you know, if you had done this, and I showed him, because I got the answer in about, the entire answer in about 30 seconds. He'd been working on it for about 20 minutes and we weren't done. And because he wasn't very good with matrix algebra, he was a statistician. And I said, if you did this, he went, did you make that up yourself? I go, no, this is kind of the standard way most people do it, the pick numbers. He's like, he literally hugged me. He was so happy. He goes, I've been doing this for 40 years. I didn't know there was, he was doing everything